You may recall several months ago we learned Newton's laws. The most mathematical of Newton's laws was Newton's second law that said that the acceleration of an object depended on the net force acting on the object divided by the mass, which is a measure of its inertia. There's an equivalent in rotational motion. Rotational dynamics, as opposed to linear dynamics, says that the angular acceleration of an object depends on the net torque acting on the object over its measure of inertia. Now the symbol we use for the measure of its inertia is a big capital I, and I'll get more into that in a moment. In order to produce an acceleration on a rotating object, you have to have a net torque. If the net torque is 0, you'll get no acceleration. The inertia is measured by a quantity known as the moment of inertia. The moment of inertia is interesting. It depends on the mass of the object, but not entirely on the mass of the object. So for instance, if I have an object that consists of, say, a very, very thin rod that connects a point mass on the end, and this is my axis of rotation here in the center, a distance r away, the amount of inertia or resistance to a change in rotation of this object would be equal to the mass of that object times the radius squared. Not only does the mass matter in this situation, but how far away it is. The further away we put this mass from the center of rotation, the more it resists rotation. You're going to do a lab where you get to feel this firsthand. That's for the simple case of a point mass. Other shapes have different moments of inertia. If you take the idea that the further away the mass is from the axis of rotation, the more it resists rotation, you can apply that to shapes as well. So say for instance, I have a solid disc and what we'll call a hoop, which is hollow in the middle. Now, if you look at the object that's solid and the object that's a hoop, and you ask yourself, which one of these has its mass further away from the axis of rotation, which we'll assume to be the very center of these objects, I think you could see that the hoop is the one that has its mass concentrated further away from the center. It turns out that if you were to spin this hoop, let's imagine this hoop and this disc have the exact same mass and the exact same radius, it would actually take more torque to achieve the same angular acceleration with the hoop than it does the disc. And there are formulas that will allow you to calculate the moment of inertia for various shapes. If you look in your packet for this chapter, I included a table that shows all the formulas. You can derive all these formulas using calculus, but I'm sure you guys are not interested in doing that, and that's because this is not a calculus-based physics class. For this hoop here, the moment of inertia would be mr squared, just like the point mass, because if you think about it, all the mass is as far out as it can get. It's similar to a point mass. It's just a bunch of point masses. But because this disk concentrates some of the mass towards the center, it only has half the inertia of the other shape. So not only does the mass matter, but the distribution of the mass matters. Now, if you have to find the moment of inertia of several objects, and let's think of these as maybe point objects. Let's say I had a very thin rod connecting 2 point masses. Let's say I'm going to rotate this object about an axis that goes through the center here. The moment of inertia of this one is mr squared. The moment of inertia of the one on the left is also mr squared. So the total moment of inertia of this object would be mr squared plus mr squared, or 2mr squared. Now this can get weird. What would happen if I move this axis of rotation? So let's say I move the axis of a rotation closer to one of the masses. What I'm going to have to do now is know what r1 is and what r2 is, and the total moment of inertia of this object now would be mr1 squared plus mr2 squared. And you could take this out almost to infinity. As long as you take each object in your diagram, figure out how far away it is from the axis of rotation, then you can sum up all the moments of inertia for each object in the array, and you'll have the total moment of inertia. The unit for moment of inertia is simply the unit of the variables in the formula. So for mass we have kilograms, and for distance we have meters squared. Now you could be asked to do problems that incorporate ideas that we've done before with this new idea. Let's say you had a problem involving a spinning object, and some of the things you knew in this problem were the initial velocity of the object, the final velocity of the object, the torque being exerted on the object, the net torque I should say, and the moment of inertia of this object. And you were being asked to find the time it would take to get from this initial speed to this final speed. And you went digging around in your kinematic equations, and you found that the final speed equals the initial speed plus the acceleration times time. This would work great as long as we knew the acceleration. But since we know the torque and the moment of inertia, we could find that acceleration by taking that net torque, dividing it by the acceleration, taking that result, putting it in here, and solving for time. This is not much different than what we did back when we learned Newton's second law.